Hello everyone, my name is Chen, and I am a PhD student from Vicens Group, Trinity College Dublin, under the supervision of Professor Aljosa Smolic. Now please allow me to present our work, a study of efficient light field subsampling and reconstruction strategies. At the beginning, I would like to give you a bit background knowledge about what is light field. According to definition, a 4D light field is defined as all light rays passing through a given amount of 3D space. In the practice, how could we capture one light field? The light field can be captured by specialized imaging system, such as camera array or lateral camera, which is shown as a figure in the upper right corner. Then, the output light field data can be represented as a collection of images arranged on a 2D matrix with a slight horizontal and vertical perspective shift, which is shown as figures in the lower right corner. Then, let me explain the issue about light field resolution we are facing here. Generally, an ideal light field is expected to have a high definition at all four dimensions, which includes S and T as angular dimension, X and Y as spatial dimension. However, in practice, when we are trying to capture one light field with a camera array-based imaging system, we can only get sparsely sampled light field, such as the one on the left, that may have equally well spatial resolution, but lower angular resolution. This is because it is an array of high-performance DSLR cameras on each perspective location, but limited of numbers of cameras can be set up. Thus, one problem appears, which is how could we reconstruct high angular resolution light field from those captured data using software algorithms. Our target is to improve the performance of the light field subsampling and reconstruction between sparse and dense light field. Multiple work has been done to reconstruct the dense light field. Some of them are based on epipolar plane image, aka EPI, such as the LF-EPI method and the ShareLight method. The others focus on utilizing the end-to-end neural network. For example, LBVS is a depth-based view synthesis network, and 4D CNN is a more recent depth-independent network. Although those state-of-the-arts have achieved an impressive performance on the light field reconstruction task, only limited attention has been paid by them to the view selection strategies. And all those previous work only arbitrarily select one fixed input strategy. For example, the reference LBVS uses 4 corners to generate a complete light field, but it doesn't discuss the possibility when applying other strategy, such as along rows and columns. Meanwhile, other row-wise and column-wise based papers also don't mention the impact once they change the order to process row and column. So in this study, we investigate the light field subsampling and reconstruction strategies and evaluate their performance. Here are 3 steps of our study. First, a benchmark method is required to compare these strategies. We will evaluate the state-of-the-art light field subsampling and reconstruction methods and choose the best performing approach. Our benchmark for following experiments. Second, since the light fields contain a huge amount of data, which pose challenges for storage and the transmission of light fields. Thus, efficient subsampling methods are needed for light fields. Given a dense light field as input, we investigate which subsampling strategy can produce the best reconstruction results while keeping a satisfying sampling ratio. Third, we also investigate different strategies for the very important task of reconstructing a lead field from corner views of a sparse lead field. So let's enter the first part, the benchmark selection. To satisfy the requirement of following experiments, our target benchmark method has to be flexible to work in different configurations. In the meantime, it also should provide the best possible interpolation qualities, of course. We therefore select two state-of-the-art lead field reconstruction method. One is deep learning based LFEPI method, and the other is non-deep learning based Charlotte method. Besides, another method called Simple Convol, which is originally designed for video interpolation, is selected as it have a flexible input pattern and it can be easily applied to lead field reconstruction problem. Oh, by the way, this application of Simple Convol on lead field actually inspired our next paper, which is called Self-Supervised Lead Field View Synthesis using Circle Consistency, that is accepted at the MMSP this year. If you are interested, this paper can be easily found on our website or archive or research kit. Please have a look. So one thing worth to mention before we introduce our first result is in this presentation we will show the results immediately following the introduction of each part of this study, instead of gathering them together at the later chapter, because each result of each previously part has influence on the next experiments. Okay, so let's discuss this comparison between the various lead field reconstruction methods. As we can see, the Simple Convol outperforms others significantly on both real-world and synthetic datasets. Therefore, we can decide to use Simple Convol as our benchmark in the further experiments. As we mentioned before, since Simple Convol was originally trained for the video frame interpolation, we additionally fine-tuned the pre-trained mode on our lead field training dataset in order to further improve the performance, push the boundary. This table shows the improvements we can achieve by fine-tuning and retraining the initial network model. After we confirmed our benchmark method, let's enter our second part, the study of subsampling strategies. As we mentioned, subsampling is widely used for practical applications such as lead field compressing or camera array design and more. So in this part of study, we evaluate the subsampling strategies by applying wheel interpolation on each sampled lead field, and then compare the quality of the reconstructed lead field and ground truth. We select three typical subsampling strategies to evaluate as they have a similar input ratio, which is a kind of sampling ratio. So row-wise, column-wise, and checkerboard is shown in these slides. And the results of these three typical subsampling strategies are shown in this table. Row-wise interpolation strategies achieves the best scores on most lead fields over all datasets, including HCI, Lecture, and Stanford dataset, both in real-world and synthetic dataset. One thing worth to note is the difference to column-wise is most significant for the Stanford data, which was captured by a gantry-controlled camera, resulting in unequal vertical displacement compared to the horizontal displacement. Okay, now let's move to the last part of the study, the reconstruction strategy study. In this set of experiments, we compare different reconstruction strategies for sparse lead fields. Taking a 3x3 matrix of views as example, 6 progressive reconstruction strategies can be applied as present in this figure. Please note the green square is the input views, and different color of circles represent output views from different stages. Using four-corner images as input, we can reconstruct the side image using the same row-wise and column-wise interpolation as before. Thus, the question becomes which is the best way to reconstruct the central view. Three of these strategies, including 2D horizontal vertical, also named 2D way, 2D vertical horizontal 2D VH, and 4D omni. Those three strategies are two-stage cases involving generated side views as intermediate stages. The other three, including 4D diagonal, 2D left diagonal, and 2D right diagonal, require only one stage to generate the central view. And here is the result of sparse light field reconstruction strategies are shown in this table. As we can see, 2D HV performs best, as it accumulates less error than other strategies with two stages, while it also have a smaller distance between input views compared to direct diagonal strategies. The visual result of reconstruction strategies are also present in this figure. We can see 2D HV has best visual results. Some occlusion artifacts around the tip of sword can be observed easily in those three diagonal strategies. To further study the influence of the angular density of the input views, we investigate three-level density as shown in this figure. The distance between two input views is one view in level 1, and there are 3 views and 7 views distance in levels 2 and 3, respectively. To compare fully reconstruct light field, we can reconstruct all missing views using appropriate strategies as follows. Level 1 is completed by row-wise and column-wise interpolation of the side views, using the 2D HV method, which is the best performing strategies to generate the central view. For level 2 and 3, we recursively fill the lower level method to complete the full-scale light field. Finally, the effect of the different levels of angular density is studied in this table. We get the expected decrease of interpolation quality with sparsity. This insight about the sparsity versus quality and the best sample sampling and reconstruction strategy can be beneficial for the design of light field coding approaches or camera system. At the end, after the introduction of all the parts of our study, let me talk about future work. The first future work could be a more clear analysis regarding the relationship of the disparity range to the strategy selection. This is because we don't involve in this disparity information in this study, but they may have some influence on some specific tasks. The other future work could be exploring the possibility to apply this study to improve practical applications, such as light field coding and light field depth estimation. And that's all. Thank you for your listening.